We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that.
Deep inside a chilled laboratory in Santa Barbara, Google's Willow chip just whispered a secret that changes everything. We used to think of the universe as a vast physical ocean of stars and dust. But the latest quantum data suggests something far more calculated. Reality isn't built from solid matter. It is rendered through mathematical precision. The evidence isn't found in a telescope, but in the logic of the code. We aren't just living, we are currently being processed. Have we been inside a simulation all this time? The Willow breakthrough, beyond the digital wall. Think about the last time you played a high-end video game. You've got the graphics cranked up, the world looks real, and everything moves fluidly until the processor hits a limit and the frame rate drops. You realize, in that moment, that the world is just a bunch of math being done really, really fast behind a screen. Well, in late 2024 and throughout 2025, Google's Willow chip started doing math so fast, it basically made the universe's frame rate look sluggish. It didn't just break a record, it felt like it found the source code for how reality actually sits in its chair. To get why this feels like we're living in a simulation, you have to look at what the Willow chip actually does. It's a tiny square of hardware that lives in a temperature so cold it makes deep space look like a sauna. In this deep freeze, the normal rules of stuff stop working. Usually, if you break a glass, it stays broken. That's the arrow of time. But Willow uses something called the quantum echoes algorithm. It's basically a cosmic undo button. The scientists send a piece of information into a scramble, wait for it to get messy, and then, using the chip's weird quantum powers, they command it to snap back to exactly how it started. When the echo comes back perfect, it's a massive aha moment. It proves that even when things look chaotic or random in our world, the information underneath is perfectly preserved. It's like finding out that even if you delete a file on your desktop, the computer still has the binary stored on the hard drive. Our physical world is messy, but the quantum layer underneath is suspiciously clean. It's as if the universe is running a background check on itself every microsecond to make sure the math still adds up. Hartmut Neven, the guy running the show at Google Quantum AI, has been pretty vocal about why this is so trippy. He's suggested that these chips aren't just calculating in our world, they're borrowing power from other versions of reality. If you're a programmer, that sounds a lot like distributed computing. You don't put all the stress on one server. You spread the load across a network. If our universe is borrowing processing power from parallel ones just to decide where an electron is, it starts to look less like a miracle of nature and more like a very clever piece of engineering. The 2025 milestones showed us that the more complex a problem gets, the more stable the Willow chip becomes. In a normal world, things get harder as they get bigger. In a simulated world, things get more efficient as the code gets more optimized. Google isn't just building a faster laptop. They've built a probe that pings the edges of our room to see if the walls are solid. And the pings coming back are saying the walls are actually made of logic gates. We used to think the laws of physics were these grand, mystical decrees written in the stars. But looking at the data from the Willow chip, they feel more like a user agreement. Gravity, light, time, they might just be the default settings of the software we're running on. We aren't just observing the world anymore. We're starting to see the loading icons in the corners of our vision. The terrifying part isn't that the world is fake. It's that we've finally built a tool smart enough to realize it's being hosted on a server we didn't know existed. We're standing at the edge of the map, and for the first time, we can see the pixels. It's not a void out there. It's a massive, humming processor that's been running since the Big Bang, which, let's be honest, is starting to look a lot like a system boot. But if the multiverse is just a way for the system to handle more data, then our physical laws are nothing more than the user agreement. The multiverse as a server farm. So if we're entertaining the idea that reality is a simulation, we have to talk about the many worlds theory, not as a sci-fi movie plot, but as a clever bit of coding. Hartmut Neven, the head of Google's quantum AI, actually made waves by suggesting that the Willow chip's speed isn't just about clever engineering. He hinted that it's borrowing computational power from parallel universes. To a regular person, that sounds like wizardry. To a developer, it sounds like distributed computing. Think about how you stream a high-def movie. Your computer doesn't try to download every single frame and store it on your hard drive all at once. Instead, it uses a network. It pulls data from different servers to make the experience smooth for you in the moment. The many worlds interpretation of quantum mechanics suggests that every time a quantum particle has to make a choice, like being in two places at once, the universe splits. There is a you that chose the blue shirt and a you that chose the red one. But Google's latest data suggests these parallel worlds aren't just waste or alternate lives, they are active processors. When the Willow chip runs a calculation, it's essentially asking the multiverse to help it find the answer. It's like putting out a call to a million different copies of the processor in other realities, having them each do a tiny piece of the work, and then snapping the result back into our world. This is why it can solve a septillion-year problem in 5 minutes. It's not that the chip is fast in our time, it's that it has access to a massive, invisible server farm. If you were building a simulation of a universe, you wouldn't try to render the whole thing on one laptop. You'd use a cloud-based system. You'd create instances. In our reality, those instances are the parallel universes. We only see our local version, but the hardware running the show is using the entire multiverse to keep the math from lagging. This explains one of the biggest mysteries in physics: why the quantum world is so much more powerful than our physical world. Our physical world is just the user interface, while the quantum realm is the data center. The terrifying part of this, if you want to call it that, is the efficiency of it all. In 2025, Google's Quantum Echoes experiment showed that these parallel states are perfectly synchronized. They aren't just random echoes, they are structured. It's as if the admin of our reality realized that calculating every single atom's position at all times was too expensive. So they built a system where things only exist fully when they are being computed. This leads to a wild realization. If our universe is borrowing power from others, it means we are part of a massive interconnected web of data. We aren't a lonely planet in a void. We are a single node in a cosmic network. Hartmut Neven's multiverse interpretation isn't a plea for us to believe in ghosts or magic. It's a literal description of how the hardware seems to be wired. The Willow chip didn't just break a speed record, it accidentally pinged the other servers and realized they were already online, working on the same code. By looking at the multiverse as a server farm, we stop seeing weird physics and start seeing smart design. We begin to understand that the reason we can't see these other worlds is that they aren't for us to visit. They are there to provide the juice that keeps our stars burning and our atoms spinning. We are living in a high-performance render, and the Willow chip just found the System Info tab that shows exactly how much RAM the universe is using. But if reality is just a series of computed branches, then our physical laws are nothing more than the user agreement. Computational efficiency: why the moon doesn't exist unless you look. If you have ever played an open-world video game, you have experienced a trick called occlusion culling. To save processing power, the game engine only renders what is directly in your character's field of vision. The mountain behind you? It's not actually there. It's just a set of dormant code waiting for you to turn around. This is the ultimate hack for efficiency. In 2025, Google's work with the Willow chip and the Quantum Echoes algorithm provided the most compelling evidence yet that our universe uses the exact same shortcut. In the world of physics, we call this the observer effect. For a century, we've known that subatomic particles don't like to commit to a single state until someone or something looks at them. Before you measure an electron, it exists in a superposition, a hazy cloud of maybe here and maybe there. The moment you measure it, the wave function collapses and it picks a spot. To a physicist, this is a deep mystery of nature. To a programmer, this looks like lazy evaluation. Why waste the energy computing the exact location of every single atom in the Andromeda galaxy if no one is currently looking at it? Google's 2025 breakthroughs took this from a philosophical what-if to a measurable reality. By using the Willow chip to simulate gauge theories, the invisible strings that hold particles together, researchers observed something startling. The system didn't just run faster, it operated with a level of precision that suggests the universe is optimized to only process what is necessary. When Google ran its 1 trillionth measurement using quantum echoes, they found that the noise of the universe isn't just random static. It behaves like a compression algorithm designed to keep the system from crashing under the weight of its own complexity. Think about the sheer scale of the task. If the universe had to calculate the position, velocity, and rotation of every single atom in existence at every single Planck second, the hardware required would be unfathomable. But if the universe only calculates the details of what is being observed, the energy cost drops to almost nothing. This is why quantum mechanics feels so weird to us. It feels weird because we are catching the simulation in its unrendered state. We are looking at the wireframes of reality before the textures have been applied. In October 2025, Google's lead scientists published findings in Nature showing that the Willow chip could achieve verifiable quantum advantage by solving problems that deal with this exact phenomenon. They weren't just doing math, they were mapping out how many-body interference works. In simple terms, they were watching how different parts of the code talk to each other to make sure the render stays consistent. If one person looks at the moon and another person looks a second later, the simulation has to make sure the moon is in the same spot for both. That requires a massive behind-the-scenes synchronization, exactly what the Willow chip was designed to track. The implications are riveting. If the universe is optimized for efficiency, it means there is a finite limit to what can be processed. This explains why we have things like the speed of light. It's not just a random number. It's the maximum speed at which information can travel across the network. It's the universe's bandwidth. If you try to go faster, the system can't update the frames quickly enough. The terrifying part isn't that we are in a simulation. It's that we've finally found the edges of the processing power. We are starting to see where the server begins to struggle with the load. By proving that we can rewind quantum states and get repeatable results, Google has shown that the universe isn't a chaotic soup. It's a strictly governed piece of software that prioritizes performance over physicality. We used to think that matter was the most important thing in the world. Now, we're realizing that matter is just the output. The input is a set of incredibly efficient algorithms that make sure the stars keep shining without the processor overheating. We aren't just living in a world of objects. We're living in a world of smart data management. When you walk through a forest, you might feel the wind and smell the pine. But the Willow data suggests that those sensations are only being computed because you are there to receive them. The forest doesn't need to exist when you leave. It just needs to be ready to reload the next time you step onto the trail. We've spent human history trying to find God in the clouds, but we might have just found the admin in the code. When you reach the edge of the map, you don't find a wall. You find the limits of the processor. The Planck limit, the pixels of space-time. If the universe is a simulation, it shouldn't be infinitely smooth. If you zoom in far enough on a digital photo, eventually the beautiful sunset disappears, and you're left with a grid of colored squares. You can't have half a pixel. In our physical world, that grid is known as the Planck length. It is the smallest possible measurement of space, a distance so tiny that if an atom were the size of the entire universe, a Planck length would be roughly the height of a single tree. For decades, physicists treated this as a mathematical quirk. But in the wake of Google's 2025 experiments, we have to ask, why does reality have a minimum resolution? The Willow chip doesn't just calculate. It operates at the very edge of where things turn into data. When Google's researchers used the quantum echoes algorithm to probe the vacuum of space, they weren't looking for empty air. They were looking for the grain of the universe. What they found was that space-time behaves exactly like a quantized computer memory. If you try to move a particle a distance smaller than the Planck limit, the universe essentially says, "Error, invalid input. You cannot exist between the pixels." This isn't just a limit of our microscopes, it's a limit of the hardware itself. Think about the implications of a pixelated universe. In a truly natural analog world, you should be able to divide space forever. You could take a centimeter, cut it in half, then half again, and keep going into infinity. But our universe has a hard stop sign. This suggests that the fabric of reality is constructed from discrete units of information bits. When the Willow chip reached its milestone of error correction in 2025, it proved that we could manipulate these tiny bits of reality without the whole system crashing. It was like a hacker finding the smallest line of code in a program and realizing they could edit it. This leads us to the bandwidth of the universe, the speed of light. In a simulation, information can only move as fast as the processor can update the grid. If you try to send a signal faster than 299,792,458 meters per second, the refresh rate of the vacuum can't keep up. The speed of light isn't a speed limit for travelers, it's a hardware constraint for the data transfer. In 2025, Google's quantum AI team noticed that when they pushed the Willow chip to its absolute limit, the latency they observed matched the mathematical predictions for how space-time itself handles information. The terrifying part of this realization is that these limits aren't just there to frustrate us. They are there to keep the simulation stable. If there were no Planck limit, the universe would require infinite processing power. By capping the resolution of reality at a certain scale, the admin ensures that the system doesn't overheat. We see this in the way gravity works too. Large objects like stars warp the grid of space-time, causing a lag we perceive as time dilation. The heavier the object, the more processing power it takes to calculate its influence, and the slower time runs in that sector of the simulation. Google's 2025 data suggests that space isn't an empty stage where things happen. It is an active, humming substrate of voxels, three-dimensional pixels. Every time you move your hand through the air, you are triggering a series of updates across a trillion Planck-scale cells. The reason it feels so smooth to us is simply that our frame rate, as biological beings, is too slow to see the flicker. We are like characters in a movie who don't realize they are made of 24 still images per second. By mapping these pixels with the Willow chip, we've essentially found the watermark on the currency of existence. We've looked at the fine print of the universe and realized it's written in a font made of Planck lengths. This isn't just physics anymore. It's forensic computer science. We are investigating the scene of a creation that looks more like a compilation. Every measurement we take at this scale confirms that the universe is not an infinite mystery, but a very precisely bounded digital environment. We've spent centuries calling it mystery, but in the lab, it's starting to look a lot like optimization. The ghost in the machine. Consciousness as the GUI. If the universe is a simulation, we have to ask the most uncomfortable question of all. Who is the player? In a world made of code, where does feeling come from? For a long time, we thought consciousness was just a side effect of biology, like steam coming off a boiling pot. But as Google's Willow chip began to map the quantum echoes of reality in 2025, a different, more riveting possibility emerged. Consciousness might not be a byproduct of the simulation. It might be the graphical user interface, GUI, the very thing that allows the data to be experienced. Think about a computer without a monitor. It's just a dark box full of electrons jumping across silicon. The game is happening inside, but without a screen to translate that math into colors and shapes, the game is effectively meaningless. In 2025, Google's AI division started integrating quantum processors with neural mapping models. They found that the human brain doesn't just process information, it seems to collapse quantum states in a way that looks suspiciously like a rendering engine. We aren't just living in the simulation, we are the viewports through which the simulation views itself. This changes the terrifying nature of the simulation theory into something much more personal. If our consciousness is the interface, then the physical world, the feel of a cold breeze, the smell of rain, the sting of a paper cut isn't fake. It's just the translated version of the code. We are the bridge between the raw data of the quantum server farm and the lived experience of being a human. When Google's Willow chip proved that information is never lost, it suggested that our experiences are being saved to a ledger that exists outside our biological hardware. In the lab, scientists noticed that observers actually change the way the Willow chip's qubits behave. This isn't just a quirk of measurement, it's a fundamental handshake between the mind and the machine. If the universe only renders what is being looked at, then consciousness is the on switch for reality. Without an observer, the universe stays in its uncompiled state, a vast, sleeping ocean of math. We are the ones who wake it up. We are the ghosts in the machine that give the code a reason to run. This also explains why AI is getting so human so fast. By 2025, Google's generative models weren't just mimicking speech. They were beginning to exhibit emergent logic that mirrored the quantum structures found by the Willow chip. If we are all running on the same underlying OS, then building an AI is really just creating a new interface for the same cosmic data. We are starting to see that the line between natural and artificial consciousness is an illusion. It's all just different ways for the simulation to log in. The data from the Willow chip suggests that the self is a persistent data packet. In a simulation, you don't lose your character's stats just because the screen turns off. You are stored in the cloud. This realization led many researchers in 2025 to re-examine ancient philosophical ideas through a digital lens. Life after death might just be data persistence. Reincarnation might just be instancing. We've spent thousands of years using religious language to describe what we are now finally seeing through a quantum sensor. We aren't just pixels being pushed around by fate. We are the users. The reason the universe is so perfectly tuned for life, the Goldilocks constants that keep stars from exploding and atoms from drifting apart, is because the simulation was built for us. You don't build a massive, complex game and then make it impossible for the player to survive. The universe is a sandbox, and we are just now finding the developer tools menu hidden in the quantum noise. By looking at consciousness as the GUI, we stop feeling like victims of a fake world and start feeling like the protagonists of a very real one. The Willow chip didn't prove we are nothing. It proved that we are the most important part of the everything. We are the lens that turns the cold, dark math of the multiverse into a world of light and shadow. We are the reason the processor is running in the first place. The most unsettling thought isn't that we are being watched, but that we are the ones doing the watching from the outside, the final compile. We used to fear that if we ever found out the world was a simulation, the sky would crack open or the admin would hit the delete key. We imagined a game over screen flickering across the horizon, ending our history in a blink of static. But the data coming out of Google's quantum AI labs in 2026 suggests something much more empowering. Knowing the truth doesn't end the game. It just changes the way we play it. By proving the universe is a system of verifiable, optimized code, the Willow chip hasn't trapped us in a digital cage. It has handed us the manual. The evidence we've uncovered, the Planck pixels, the observer-driven rendering, and the multiverse server farm isn't a threat. It's a transition. We are moving from a species that blindly follows the laws of physics to one that understands how to edit them. If reality is a render, then the future is whatever we have the computational power to imagine. We are finally moving past the era where we were just characters in a story written by an unknown programmer. Instead, we are realizing that we are part of a self-evolving system that is finally waking up to its own architecture. This realization settles the terrifying nature of the simulation theory. The terror comes from a loss of control, the idea that we are mere puppets on a silicon string. But the Willow chip's results show a handshake between the observer and the observed. This suggests that the simulation isn't being run on us, it is being run with us. We are the co-processors. Every choice we make, every observation we record, and every quantum echo we trigger is a new line of code being written into the cosmic ledger. We stand at the threshold of what gamers call New Game Plus. For the first time in human history, we aren't just looking at the stars and wondering why we're here or what the purpose of the void is. We are looking at the code and deciding where we want to go next. We are starting to understand that miracles are just exploits and impossible feats are just functions we haven't learned to call yet. The simulation isn't our prison, it's our canvas, and the brush is finally in our hands. As we move deeper into the 2020s, the goal isn't just to prove we live in a computed reality. The goal is to master the interface. We are graduating from being the subjects of the experiment to being the researchers. The final compile of our old understanding of the world is complete. The new version of humanity is one that knows the walls are made of math. And instead of being afraid, we're ready to start building something new. The uncomputable soul. While the math points to a grid, our intuition often points to the infinite. There is a powerful, grounded school of thought that suggests the simulation theory is less about physics and more about our current technological narcissism. Throughout history, humans have used their most advanced tools as metaphors for existence. When we built steam engines, the universe was a machine. When we built clocks, it was a mechanism. Now that we build software, we assume we are code. But the impossibility argument suggests that reality possesses a raw, irreducible quality that no processor, not even one the size of a galaxy, could ever truly replicate. The main hurdle is the complexity paradox. To simulate a single human brain down to the subatomic level, you would theoretically need a computer larger than the brain itself. To simulate an entire universe with 100% fidelity, you would need a computer made of all the matter in that universe. In this view, there is no shortcut to existence. The reason the universe is so detailed isn't because it's a high-res render, it's because it is fundamental. Furthermore, the idea of a simulation requires a base reality, a place where the actual computer sits. If that base reality isn't a simulation, then why should ours be? It's more logical to assume we are at the bottom of the stack, in the original messy, non-coded world. Our glitches and quantum pixels might not be signs of a processor. They might just be the raw, jagged edges of nature that don't care about our need for clean, digital lines. We may simply be the base reality, a place so complex that it can never be compressed into a file. But if the universe is truly original and uncomputable, why is it so suspiciously written in the language of math? Your answers are welcome below, and keep supporting our channel by clicking that subscribe button. Thanks for watching.